Voyager 1 and 2 have made impossible discoveries after 45 years in space. At present, Voyager 1 and Voyager 2 spacecraft have turned off all their auxiliary devices to save energy for their journey through interstellar space. This indicates that they have completed their mission of exploring the distant planets within our solar system and are now venturing into the vast unknown universe. Their accomplishments stand as a testament to humanity's unwavering efforts to explore the cosmos beyond our solar system. Despite their limited memory capacity, which is over 3 million times smaller than that of a typical smartphone, and an internet connection that is 38,000 times slower than 5G, these remarkable probes continue to lead the way in space exploration. After 45 years of accompanying humanity on a journey to distant planets, both spacecraft have now powered down their entire systems in preparation for their eternal cosmic solitude. What does the future hold for them? Where are they now, and what lies ahead for these spacecraft? Join us in today's video as we take a trip down memory lane to reflect on their past and speculate about their upcoming future. Voyager 2's untold incidents. Voyager 2 stands out as a space probe with a rather comical fate, encountering some unbelievable hiccups due to human-operated system maneuvers. Its somewhat ironic destiny began right from its launch. Initially, the launch process went smoothly without any hitches. However, a few weeks later, the ground control team of the Voyager program faced an issue. They had forgotten to send a crucial software upgrade to Voyager 2 after the initial launch with Voyager 1. This oversight caused Voyager 2 to shut down its primary radio receiver and switch to using a similar backup device, resulting in a minor malfunction. During the switching process between the two receivers on several occasions, a fuse in the main power supply of the primary receiver blew, rendering it permanently non-functional. Henceforth, the entire mission had to rely on the backup receiver. However, there were other challenges. During the launch of the Titan Centaur rocket carrying the Voyager 2 spacecraft, the spacecraft's computer encountered an unexpected robotic imbalance. This led to the unnecessary activation of backup sensors, causing the primary sensors to cease functioning. The flight control computer lost orientation, but the Centaur's attitude control system maintained stability. After separating from the rocket, Voyager 2 autonomously oriented itself and transmitted a radio signal indicating normal operations. Engineers couldn't monitor and rectify the issue directly, but ultimately, the computer self-repaired due to a minor misconfiguration in the attitude measurement device. Voyager 2 was programmed to autonomously address problems and, in case of emergencies in deep space, cut communication with Earth. Next came another peculiar incident on July 21, 2023. At that time, engineers inadvertently sent the wrong command, causing the spacecraft's antenna to deviate from Earth by about 2 degrees. This disrupted the connection between the spacecraft and NASA's Deep Space Network. This was the sole rare incident in the 46 years of the mission. NASA reported that its giant dish antenna in Canberra, Australia, is searching for signals from the Voyager 2 spacecraft, which is more than 19 billion kilometers away from Earth. It takes over 18 hours for signals to reach Earth from such a vast distance, and they anticipate re-establishing contact with Voyager 2 by October 15th. However, the spacecraft responded earlier than expected. Specifically, Voyager 2 began transmitting data back to Earth on August 4th. NASA's Jet Propulsion Laboratory, JPL, received a heartbeat signal from the spacecraft on August 1st, allowing mission controllers to know that the probe is still functioning well, even though full communication with it is not possible. Voyager 2 is programmed to adjust its orientation a few times a year autonomously, and the next troubleshooting adjustment is scheduled for October of this year. On August 4th, JPL announced that NASA's Deep Space Network facility in Canberra, Australia, could send commands into interstellar space to help realign the spacecraft and point its antenna back toward Earth. Mission controllers had to wait 37 hours to confirm the command's success. According to JPL, the spacecraft began transmitting scientific and observational data, demonstrating that it is operating normally and still following its expected trajectory. Scientists have estimated that both spacecraft are gradually losing power from their radioisotope thermoelectric generators, but engineers have made several adjustments to preserve the systems. The heating instruments were turned off in April 2023 as they shut down the heater on the Voyager 2 to conserve power. These measures allow the spacecraft's power supply to last longer, extending data collection until at least 2026. Throughout its journey, Voyager 2 has visited both Uranus and Neptune. It is the only tool of humanity to explore these two planets in the 20th century. In November 2018, NASA announced that the spacecraft had crossed the outer boundary of the solar system, with Voyager 1 having crossed this boundary in 2012. The continued operation of both spacecraft after 45 years surpasses the predictions of mission planners. Suzanne Dodd, project manager for Voyager 1 and 2 at NASA, said, "This is a mystery that was not predicted throughout the Voyager mission." Special structure of Voyager 1 and 2. Even though it's been nearly half a century, the intricate design of Voyager 1 and Voyager 2 continues to serve as an inspiration for many future generations of space probes. Voyager 1 was built at the Jet Propulsion Laboratory, JPL, a government-funded research and development center specializing in NASA's propulsion systems, located in Pasadena, California. The spacecraft has a hollow hexagonal structure with a total of 10 compartments along the edges to house electronic equipment, while the central hollow part is used for fuel storage. On board, there are only 11 scientific instruments designed to study objects such as planets, asteroids, etc. as it travels through space, simultaneously sending data back to Earth. To observe the planets along its journey, Voyager 1 is equipped with two main cameras, including one with a 200mm focal length f3 aperture and another with a 1500mm focal length f8.5 aperture. Both cameras are equipped with 8 color filters and use an improved version of the Vidicon sensor used in Mariner spacecraft cameras to capture images. The entire operation is controlled by the spacecraft's FDS computer system. The spacecraft's power is supplied by 3 radioisotope thermoelectric generators, RTGs, using plutonium as the primary element. According to NASA data, the RTGs were capable of generating around 470 watts of electricity at the time of launch. The power output of the RTGs is expected to gradually decrease over time due to the extended decay cycle of plutonium-238, as well as the diminishing efficiency of the thermoelectric couples. Although both Voyager 1 and Voyager 2 were designed with the intention of flying by both Saturn and Uranus, at that time, few could have anticipated that they would still be operating well after more than 4 decades. Designed to explore the distant reaches of space, Voyager 1 has exceeded NASA's expectations, currently residing about 23.5 billion kilometers from Earth, equivalent to more than 157 times the distance to the Sun. The spacecraft is also moving farther away at an average speed of 60,000 km/h. Meanwhile, Voyager 2 is positioned approximately 18.9 billion kilometers from Earth, pointing towards the Sagittarius constellation. The 45-year journey of Voyager 1. Throughout their extraordinary journey, both Voyager spacecraft have provided humanity with unprecedented observations of the unexplored cosmos. Following its successful launch in 1977, Voyager 1 began capturing images of Saturn in January 1979. Its closest approach to Saturn occurred on March 5, 1979, at a distance of approximately 349,000 kilometers, 217,000 miles, from the planet's center. Due to the increased image resolution at closer proximity, the majority of observations of the moons, rings, magnetic fields, and radiation belts of the Saturnian system were conducted during the 48-hour period of this closest approach. Voyager 1 concluded its imaging of the Saturnian system in April 1979. Under remote guidance, Voyager 1 made several significant discoveries about Saturn, its moons, its radiation belts, and its previously unseen planetary disks. The most remarkable discovery about the Saturnian system was the presence of volcanic activity on the moon Io, something that Earth-based observatories and Pioneer 10 or 11 had never observed before. Io is the first known natural satellite with peculiar volcanic surfaces. In November 1979, Voyager 1 continued its journey toward Mars and its largest moon, Titan. Meanwhile, its twin spacecraft headed for Uranus and Neptune. Voyager 1 flew past the Martian system in November 1980, with its closest approach on November 12, 1980, when it came within approximately 124,000 kilometers of Mars' highest clouds. With the help of Saturn's gravity, Voyager 1 successfully explored the moons and extensive ring systems of Mars. During this time, the spacecraft's cameras discovered complex structures within the rings of Mars, and its remote sensors studied the atmosphere of Mars along with its large moon, Titan. Pioneer 11 had discovered a dense and multi-gas atmosphere on Titan a year earlier. The Jet Propulsion Laboratory's mission controllers selected Voyager 1 to perform a close encounter with Titan, which was also essential to conclude its grand tour. Voyager 1's trajectory with a flyby of Titan created an excess gravitational deflection, causing Voyager 1 to veer out of the ecliptic plane, which ended its planetary science mission. Voyager 1 could have been put on a different escape trajectory, where the gravitational slingshot effect of Saturn's mass would have propelled Voyager 1 outward on a trajectory beyond the Kuiper belt. However, this choice was not implemented, as the trajectory passing through Titan was determined to offer additional scientific value and reduce risk. On February 14, 1990, Voyager 1 captured the first family portrait of our solar system from the outside, including the iconic image known as the pale blue dot. As of today, Voyager 1 remains the farthest operating spacecraft receiving commands and transmitting signals back to Earth. In 2012, the spacecraft officially entered interstellar space, beyond the heliosphere. This is a region similar to a bubble, formed by continuously emitted charged particles from the Sun. In this region, Voyager 1 recorded the appearance of numerous cosmic rays, or atomic fragments traversing space, intermingled with charged particles from the Sun. This marked the first time humans could directly study how a star, or our Sun, interacts with particles and magnetic fields beyond the heliosphere. On August 25, 2022, based on the data sent back by Voyager 1, NASA confirmed that the spacecraft had crossed the boundary of the solar system and was moving within an interstellar region beyond the heliosphere. This is defined as a bubble, filled with high-energy particles and magnetic fields emanating from the Sun. NASA's previous surveys also indicated the spacecraft's remaining systems were stable, continuing to collect and transmit research data to Earth. This data will help us further explore a pristine region of space, unaffected by any star. The Voyager 2 missions. Similar in design and instruments to its sibling spacecraft in the Voyager program, Voyager 2, like Voyager 1, was launched with a lower and more curved trajectory. This allowed it to be kept within the plane of the ecliptic, the plane of the solar system, to reach Uranus and Neptune using gravitational assists as it flew by Saturn in 1981 and Uranus in 1986. Due to this chosen trajectory, Voyager 2 couldn't get as close to Saturn's largest moon, Titan, as its twin spacecraft. Instead, it became the only spacecraft to conduct unmanned flybys of all 4 outer planets and their moon systems, including the first visits to Uranus and Neptune. On January 24, 1986, Voyager 2 flew within 81,500 kilometers, 50,600 miles, of Uranus's cloud tops, marking the closest approach to the planet. During the flyby, Voyager 2 discovered 10 new moons of Uranus, studied the planet's unique atmosphere, and examined its ring system. Uranus, the third largest planet in the solar system, orbits the Sun at a distance of approximately 2.8 billion kilometers, 1.7 billion miles, and completes one orbit every 84 years. Voyager 2 also measured the length of a day on Uranus, which is 17 hours and 14 minutes. Uranus is an unusual planet due to its extreme axial tilt of approximately 90 degrees, which means that its axis is almost parallel to the ecliptic plane instead of perpendicular. Scientists believe that this unusual tilt resulted from a collision with a large planet-sized object during Uranus's formation. This unique tilt poses uncertainties for planetary scientists when observing or measuring Uranus, as the polar regions remain in darkness for many years or continuously receive sunlight. Voyager 2 observed that one of the most surprising effects of Uranus's rotation onto its side is the peculiar behavior of its magnetic field. It is tilted about 60 degrees relative to the planet's rotational axis. The magnetic field's tail was found to be twisted into a long corkscrew trailing behind the planet. The presence of Uranus's strong magnetic field was unknown until Voyager 2 arrived. The radiation belts of Uranus were discovered to be as dense as those of Saturn. The radiation belt's high density inside Uranus's rings causes the radiation to quickly decay. Within 100,000 years, any trapped methane in the icy surfaces of the inner moons and ring particles. This rapid decay may have contributed to the dark surfaces of the moons and ring particles, nearly all of which are dark gray. A haze layer was identified surrounding Uranus's pole, where the sunlight is most direct. This region was also found to emit a significant amount of ultraviolet light, a phenomenon known as dayglow. The average temperature of Uranus's atmosphere is about 60 K, negative 350 degrees Fahrenheit, negative 213 degrees Celsius. Surprisingly, both the pole in darkness and the sunlit pole exhibit similar temperatures in the cloud tops. On August 25, 1989, Voyager 2 had its closest encounter with Neptune, which was the last planet in our solar system that the spacecraft could explore. To gather as much information as possible about Neptune and Triton, its largest moon, the project lead scientist, team members, and mission controllers decided to execute a flyby of Triton, regardless of the angle at which Voyager 2 would leave Neptune. This mirrored Voyager 1's encounter with Saturn and its largest moon, Titan. Before the encounter, mission controllers conducted multiple trajectory tests to determine the best approach for Voyager 2 to traverse the Neptune-Triton system. Since Triton's orbit is inclined relative to the ecliptic plane, adjustments were made to direct Voyager 2 along a trajectory well above Neptune's north pole, covering thousands of miles. At the time, Triton was positioned behind and below Neptune, near the apoapsis of its elliptical orbit. The gravitational pull of Neptune bent Voyager 2's trajectory downward toward Triton. In less than 24 hours, Voyager 2 had passed the distance between Neptune and Triton, then observed Triton's northern hemisphere as the spacecraft moved beyond Triton's northern pole. The actual effect and final adjustment on Voyager 2's trajectory involved bending its path about 30 degrees south below the ecliptic plane. Voyager 2 consistently followed this trajectory, exploring space south of the ecliptic plane. It measured magnetic fields, charged particles, and more in that region, sending telemetry data back to Earth. While in the vicinity of Neptune, Voyager 2 discovered the Great Dark Spot, which later disappeared, as observed by the Hubble Space Telescope. Initially thought to be a large cloud, the Great Dark Spot was later hypothesized to be a hole in the visible cloud layer of Neptune. The atmosphere of Neptune consists of hydrogen, helium, and methane. Methane in the upper atmosphere of Neptune absorbs red light from the sun, but it reflects green light into space. This phenomenon explains why Neptune appears blue. As its planetary mission concluded, Voyager 2 is now considered to be on an interstellar mission, exploring how the solar system is beyond the heliosphere. On August 30th, 2007, Voyager 2 crossed the termination shock, approximately 1 billion miles, 1.6 billion kilometers, closer to the Sun than Voyager 1. This is due to the local interstellar magnetic field pushing into the solar wind. The southern hemisphere of the heliosphere is being compressed. As of April 13, 2010, Voyager 2 is at a distance of about 91,898 AU, 13,147 billion kilometers, 8,142 billion miles, or 0.443 light-years from the Sun, deep within the scattered disk, and is moving outward at a speed of about 3,264 AU per year. It is twice as far from the Sun as Sedna, and outside the aphelion of 90377 Sedna, but still not beyond the outer limits of the orbit of the dwarf planet Eris. Voyager 2 is not aimed at any specific star. If left unaltered, it will pass by Sirius, currently at a distance of 2.6 parsecs from the Sun and moving away from the Sun at approximately 1.32 parsecs, 4.3 light-years, 25 trillion miles, in about 296,000 years. Voyager 2 is expected to continue transmitting weak radio signals at least until 2025, more than 48 years after it was launched. What will Voyager's fate be? Despite 45 years having passed, the electronic components of the Voyager spacecraft continue to operate remarkably well. This is because both Voyager 1 and its twin sibling are powered by plutonium, a radioactive element capable of generating nuclear energy through fission reactions. Moreover, the spacecraft's computer system requires minimal energy. According to NASA, the data collected by the spacecraft is recorded on an 8-track tape and then transmitted to Earth using a device that consumes only as much power as a refrigerator light bulb. According to Scientific American, the power output generated by plutonium on Voyager 1 and 2 decreases by only about 4 W per year, and the missions could potentially extend into the 2030s. I cannot say how long the mission will last, but the spacecraft will continue to unravel mysteries of space as it moves further from Earth, said Suzanne Dodd. However, she acknowledges that NASA will need to gradually deactivate additional instruments on the spacecraft over time, and the nuclear power source of the probes will eventually decay, ceasing to operate. Thus, there will come a day when NASA will power down the final exploration devices on the probes to conclude their historic mission, but their journey through space will not truly come to an end. Over the next 20,000 years, Voyager 1 and 2 are expected to pass by Proxima Centauri, a dwarf star in the constellation of Centaurus. They may even continue to orbit our galaxy for billions of years in a nearly pristine state, long after the Sun is no more. Both Voyager 1 and 2 have the responsibility of serving as evidence of humanity's existence. They carry a testament crafted by NASA engineers known as the Voyager disk. Initially tasked with exploring distant planets in the solar system, when it became apparent that the probes would continue their journey into space after their primary mission, scientists decided to include a message from Earth on each spacecraft as a precaution in case they were ever discovered by extraterrestrial beings. Initially planning to use only algebraic and geometric images, they found it insufficient. They decided to incorporate music and sounds from Earth to convey the essence of humanity to potential extraterrestrial life. The Voyager Golden Record contains a wealth of visual information with 115 images, 27 musical compositions, and sounds describing our planet. It includes greetings in 55 different languages from around the world. Following that are sounds from nature, the patter of rain, the rustle of the wind, the songs of birds, the most instinctive sounds we produce, like a child's laughter, or the rhythmic heartbeat of a man preparing to propose to his beloved. Interspersed are melodic masterpieces ranging from classical to contemporary music. In addition to sound, Carl Sagan and his team added images depicting life on Earth to the Voyager disk. Among these were pictures of children from different races holding hands around the globe, a symbolic representation of global peace, and an image of a teacher instructing students, recognizing the importance of education. The remarkable strides in science and technology were also showcased through an X-ray image of a woman's hand. The disc is made of gold-plated copper, with an aluminum cover electroplated by a layer of ultra-pure radioactive isotope uranium-238. Half of this uranium will decay after 4.51 billion years, allowing extraterrestrial beings, if they find the golden record, to estimate how long it has been by calculating the remaining uranium. Soon, both spacecraft will run out of energy and become drifters in interstellar space. We can only hope that another civilization will welcome the existence of a species that once thrived on the blue planet. And if, in the future, humanity faces extinction, Voyager 1 and 2 will stand as a testament to future generations that a blue orb with a developed civilization once existed and left a small imprint in the cosmos.